Hello, in this video we're going to be talking about topological spaces. So let's define what a topological space is. But in order to do that, we have to first define what a topology is. Now, a topology on a set X, we're going to call the topology tau. It's pretty standard. So a topology on a set X is a collection. I wrote set, but a collection is a little bit better because sometimes you can have sets that are so big that they're not actually sets anymore. So we have a collection of subsets of X with the following three properties. The empty set and the set itself are in the topology, and if I have an arbitrary collection of elements in the topology, then that arbitrary union is also in the topology. And finally, we have that if we take a finite number of elements in our topology, that finite intersection is also in the topology. And now when we take this set X and this topology tau, and we put them together, we get a topological space. And we just kind of denote this by the ordered pair X comma tau. And that is the formal way of writing this structure, which is a topological space. So a quick and dirty definition of a topological space is this ordered pair. So it's a set and a topology on the set. And that is what we call a topological space. So in topology, we have a concept called open and closed sets. And the concept of an open and closed set is really fundamental to topology, and fortunately, it's pretty easy to understand. So a set is called open if it is an element of tau, our topology. And it is closed if its complement is open. Now this is a little different than saying it's closed if it's not open, because topology isn't like doors. It's not just open or closed. We can have sets that are neither open nor closed, and we can also have sets that are both open and closed. So to clarify this situation, let's take a look at a couple of examples. So first, let's consider a 3-point set. So X is going to be A, B, and C. And let's first draw out what tau is before we write it explicitly. So let's have 3 points, A, B, and C, and draw them down there. And then we know that the empty set has to be in there, but we can't really draw that. And we know that the whole set itself has to be there. So let's draw a circle around the whole set. And in our topology, let's also include the singleton A and the set consisting of A and B only. So take it on faith that this is a topology. You can check it if you'd like. But what's important is, what are the open and closed sets? So the open sets are everything that's in tau. So if we just rewrite tau, we have our open sets. So our closed sets then are going to be the complements of these. So the complement of the empty set is the whole set itself, and the complement of the whole set is the empty set. So the empty set and X are both in the complement, so they're both closed. Then we can take the complement of A, that's BC, and the complement of AB, which is C. But then we have some things left over. So we have the subsets B, singleton B, and the subset AC of X. And since they're not open and they're not the complement of an open set, they are neither open nor closed. Now, there's a nice property about the empty set and X. They're both open and closed. So in topology, we call them open and closed sets in older literature, or as we like to colloquially refer them, clopen sets. And it turns out that no matter what topology we're in, since the empty set and the set itself are always open, their complements are always also the empty set and X. So the empty set and X are always clopen sets, no matter the topology. Next, we're going to take a look at two examples of topologies that I like to consider trivial. And we'll see why in a second after we actually go through the examples. But the first one, the indiscrete topology, is what is normally referred to as the trivial topology. So it's defined as follows. If we have X be equal to any set and tau equal to the empty set and X itself, that's our topological space. So we claim that tau is a topology on X. So we have to first check all of our axioms before we can conclude that this is in fact a topology. So the first one, we have to make sure that the empty set and X are in tau, and a quick check of what tau is actually defined to be gives us this almost immediately. Next, we have to check to make sure that arbitrary unions are in tau. So we have to check that X union X is in tau. We have to check that X union the empty set is in tau. The empty set union X is in tau. And the empty set union the empty set is in tau. Even though the axiom states arbitrary arbitrary unions, we have finitely many elements, and we can actually list them all out in all of their orders. So it turns out that in a finite case, we're only going to have finitely many unions. So X union X is going to be X. Same with X union the empty set and the empty set union X. And finally, the empty set union itself is empty. And all of these are in tau. So step 2, we're set on. Now let's go ahead and take a look at 3. So axiom 3 states finite intersections of elements of tau are still in tau. So we're just going to go through X intersect X, X intersect the empty set intersect X, and the empty set intersect itself. Now the empty set intersect anything is the empty set, and X intersect itself is going to be X, and both of these are in tau. This tells us then that tau is a topology. So our next example is the opposite of the indiscrete topology, creatively called the discrete topology. So if we have X equal to any set, we're going to define the topology tau to be every possible subset of X, also called the power set of X. And checking this is also fairly trivial, so we won't write it down. But X and the empty set are subsets of X, so that checks off box 1. To see that arbitrary unions are in there, if we take any combination of subsets of X, we have another subset of X. So box 2, checked. Next, we have to check arbitrary intersection or finite intersections. And if we have a finite intersection of subsets of X, it's going to again be either another subset of X or the empty set, which is still a subset of X. So the next thing that we want to talk about with topologies is comparing them. So can we say one topology is more descriptive than another? So let's talk about this a little bit more formally. So if we have X as a set, and we have two topologies on the same set, say tau 1 and tau 2, if we can compare these two topologies, we can say that one is finer than the other, or one is coarser than the other. So we say that tau 1 doesn't really matter if we choose tau 2. We say tau 1 is finer than tau 2 if tau 1 completely contains tau 2. And we say that tau 1 is coarser than tau 2 if tau 1 is contained in tau 2. The way that I think about it, and the way that several books describe it, is by thinking of a truck full of gravel compared to a truck full of gravel after it's been crushed. So if we have a truck full of gravel, we have a certain amount of stuff in it. But if we crush it, we can piece and compress together some of the dust or sand back into the original gravel pieces. But we can't take the original gravel pieces and put them together to get pieces of sand. And that's how we can think of finer and coarser, because the sand physically is finer than the coarser gravel. And we need to look no further to think of finer and coarser topologies than by looking at the discrete and indiscrete topologies. So the indiscrete topology, no matter what our set is or what our topology is, the indiscrete is always going to be the coarsest possible topology on the set. Remember, that just consists of the set itself and the empty set. So that's just like a big boulder and nothing. And the discrete topology is going to be the finest possible topology on a set. So we can think of that as like the atoms of the set. And from these atoms, we can put them together and make any other subset of X. So another example is going to be the real numbers. So we'll take X equal to the real numbers, and we'll define tau 1 to be the collection of all open sets, A to B, so open intervals, and tau 2, we'll call that, say, half closed intervals or half open intervals. Now, tau 2 is actually finer than tau 1 because we can construct open intervals from these half open intervals by just taking these unions. So we can create AB from the union of A comma B minus 1 over n, as n ranges from 1 to infinity. However, we can't create that closed interval from these open intervals. If we were to do that, we would have to take an infinite intersection of, say, A, B plus 1 over n. And while it's not a finer topology or a nice thing in elementary topology at this level, if you have taken an analysis class or you're familiar with analysis, you might recognize that intersection as a G-delta set. I made a remark that some topologies can be compared, which means that some topologies can't be compared. So if we can compare them, we call them comparable. But let's look at an example where they can't be compared. Now, an example of this is going to be let's take as our set X, the 3-element set A, B, and C. And we'll take as tau 1, the empty set X and singleton A. And for tau 2, we'll take the empty set X and singleton B. Now, tau 1 is not a subset of tau 2, and tau 2 is not a subset of tau 1. Therefore, we can't compare them, so they're incomparable. Finally, let's talk about a basis for a topology. Now, if you're familiar with linear algebra, you know that a basis for a vector space is a set that through linear combinations can create anything in the vector space. And there's kind of an analogy to topology. So a basis for a topology is a collection of subsets of X such that when we take their arbitrary unions, we can create the whole set. But there's a little extra bit of a property to it. So let's let X be a set and tau a topology on X. Now a basis then, we're going to call it a set B, fancy B, is going to be a collection of subsets of X with the following two properties. So the first property is that for any element X in our bigger set X, there is a basis element that contains it. So every element is contained in a basis set. And secondly, if I have an X, an element, in two basis elements, there's a third basis element that contains X that is a subset of the intersection of the first two. And writing it out, it looks a little clearer. So now let's look at a couple of examples. So our first two examples, we're going to be looking at the real plane, R2. And for our first basis that we're going to consider, we're going to look at all circular regions in R2, in the plane. And this does form a basis, because if I have any point, I can encompass it by a circle. And if I have two circles that overlap, I can pick any point in there and put a smaller circle so that it's completely contained in that overlap. For our second example, we're going to take a look at all square regions in the plane. And the same property pretty much holds. So if I have two squares and I overlap them, I can pick a point in that overlap and put a square around it such that it's completely contained in that overlap. For our final example, let's take a look at the discrete topology. Remember, that is the collection of all subsets of a given set X. So we're going to claim that a basis for this is the set of all singleton elements of the set. So to check this, we're going to first see that it covers the set X. So for any element in X, the singleton point containing it contains the point. So every element is in some sort of basis element. And now if we have two basis elements, say B1 and B2, then if we also have a point X in their intersection, X is contained within the singleton point, the singleton set X, which is going to be a subset of the intersection. Thank you for watching.